Okay, let us do an example. A particle is moving along the x-axis. Okay. And I measure its position at various times. At t equals 0, the position was 0, let's say. At t equals 1, position was 5 meters. At t equals 2 seconds, the position was 20 meters. Then I have some observations from the past also. At t equals minus 1 seconds, the position was, again, 5 meters to the right. At t equals minus 2 seconds, the position was 20 meters. Okay? So it came from 20 meters, 5 meters, 0, and then went back out. So the actual motion is this. Okay? This is the graph. So I have done the experiment. I have got a table of all the values of x at different times. T and I have a graph of it. And then I have played with the graph. I have made many, many measurements. And I realized that x of t actually has a nice formula. I already know, I have measured and found out that the position follows the formula x equals 5t squared. But during all of this, I only measured positions and times. So I've got x of t. I have not measured velocities. Now I can go back and look at my x1, x2, t1, t2 for various different times. I can figure out what the velocity is. And then I can try to make it with shorter and shorter time intervals. See if they exist in my data. Okay. And calculate better, more exact velocities. But in the last lecture, we thought about how to calculate exact velocity, and we wrote down what one must do to calculate an exact velocity as a function of time. So now I know the position as a function of time, and I will now use the procedure I wrote, the question I wrote in the last lecture, to see if I can get the velocity as a function of time for all different times with just one calculation. Okay? Without having to do, velocity is distance divided by time, which distance, this distance, that distance, this time. Do it again and again. Now that I know position as a function of time, and I know how one should measure or calculate an exact velocity, let me now apply this procedure and see if I can get it. Okay? So, v of t is dx dt. That's short name for it. And how do I calculate this? I will calculate x at t plus delta t minus x of t divided by delta t, and then I will see what the result of that calculation does if delta t goes to 0. Delta t is shorter than the shortest thing that we can imagine. Okay? But before taking this limit, short, shorter, shortest, I first imagine I'm doing it at some time t, and I know the value of the interval delta t, whatever it is. Okay? Let me just calculate the formula. Step by step. So this equals Now, what is x at time t plus delta t? You tell me this. Okay. We want to write a formula, an expression for x at what time? When the time is t plus delta t. Given the time in this problem, how do I find the position? It's going to be 5 times that time squared. So what shall I write here? 5 times okay, minus 5 times t squared, that's easy, divided by delta t, whatever delta t is. Okay? Yes? Any questions? In this example, the example I am giving you, I have already measured x at t, and I have made a table, I have made a graph. I know that at any time t, x equals 5 times t squared. When t was 1 second, x was 5 times 1 squared, 5 meters. When t was 2 seconds, x was 20 meters. When t was t plus delta t seconds, I don't know what t plus delta t is, then x must be, x at time t plus delta t must be 5 times t plus delta t squared in this example. Okay? So I'm just putting it in place. And now, let us start calculating. Okay? T plus delta t squared. What does that give me? Okay? Well, 5 is already there. Let me write the 5. You tell me what t plus delta t squared is. Yeah, there's a t squared, and then plus 2t delta t plus delta t square minus 5t square divided by delta t. Okay? Now let me just calculate that multiplication of the parentheses. I have 5t squared plus 10t delta t plus 5 delta t squared, and I had a minus 5t squared divided by delta t, and I shouldn't forget to write the limit here because I have not done the limit yet. I'm just doing the formula. Is this clear? Now I have a 5t squared here, and this cancels. This will always happen. The physical reason is because the position of the particle at t plus delta t is not far from the position at t. It's the position at t plus some step that it has done. So the position at t will be there to start with, and then there will be some extra terms. And that will cancel. That will always be the case. Okay? The remaining term here, after I've subtracted, taken off the initial position, the remainder is delta x, the distance it has gone from the initial position on. Okay? Now, what will happen? This equals, I will take the limit at the end, tan t now the delta x upstairs, in all of its terms it has delta t's. This tells you clearly that delta x is small than delta t is small. Exactly how it depends on delta t will depend on your problem, your example. Here I have a 10 in front, etc. In a different problem it will be different, but delta x will always have some delta t's in it. Is this clear? And the physical reason is because in a short time the distance gone is also going to be short. Okay? And those delta t's will now cancel. Clear? This becomes I had a delta t squared here, and one of the delta t's cancels.